is the point.
Please help me out.
Yes, we'll carry you.
Hold on. I got struck by lightning?
Yes.
How the fuck did that happen?
In August 2003, Matt Thompson was hit by lightning in the hills outside Keystone, Colorado.
A bolt of lightning taken straight in the chest.
It just came out of nowhere.
The direct hit traveled all the way through Matt's body.
I have no clue what happened.
Matt's story was big news. On websites worldwide, the issue was raging.
Man, you almost died.
Was Matt's metal tongue stud the reason he was struck?
It's my tongue ring.
I don't know, dude. You might have swallowed it.
Let me see. Where's your tongue? Let's see it.
All it's broken off in there, it looks like. Is it?
By jewelry attracting lightning strikes?
So, does metal on your body attract lightning? This is worthy of a discussion. Does metal itself attract lightning? Okay, let's think of it this way: the lightning rods. What's the purpose of a lightning rod? Okay, so it's some people think that it's to deflect or repel lightning. No, the purpose of a lightning rod is to attract lightning to itself, right? Lightning rods, are they made up of plastic, porcelain, metal, paper, wood? You know the answer, right? The lightning rods are made up of metal. So can we assume that because the lightning rods mean to attract lightning and they're made up of metal, does this mean that the metal is better at attracting lightning to itself? And most of you guys will say yes to that, right? So does this mean that the metal on your body also attract lightning? So there's a bit of a claim here that her, or in this case his, tongue stud is the one that attracted lightning. So does this mean that during a lightning storm, you should just probably leave your keys at home, the coins or whatnot, get rid of the jewelry? So will the metal jewelry on your body attract lightning? Okay, it's kind of weird because some of you guys will say, not very likely, because you will think that the size is going to matter. That's a common response that I get. So some will say it's not too big. It's not big enough to attract lightning. And some of you guys say, yeah, okay, it may attract lightning. I can see the problem there. All right, so, okay, Gustavo, give yourself 5 points for that remark. Okay, so another thing is high ground versus the low ground. So let's agree that the high ground is more dangerous. Okay, so there's no question about it. The high ground is going to get struck by lightning more often. Okay, so there's no denying that. So, but not 100% of the time. Okay, so if the logic is correct that the high ground is more likely to be struck by lightning because it's closer to the clouds, that should be an absolute fact, which means that the high ground should be struck by lightning 100% of the time. The tallest structures should be struck by 100% of the time. The taller people should be struck by lightning 100% of the time. That has to be an absolute statement, yet it's not. So the question is, why is it that logic does not work 100% of the time? All right, so the Sears Tower is in the background. The small building is taken in. These pictures are taken by one of my engineering students. Once again, the other buildings or places are being struck, despite the fact that the Sears Tower is in the foreground. Nothing's happening to the Sears. And okay, so this is the building where I used to live. So what's going on?
Strikes a year in the U.S., setting 1,500 fires, burning over 200,000 acres, destroying homes, $150 million worth a year. And deadly, too, killing about 100 a year in the U.S., injuring another 300. Just 10 days ago, a bolt of lightning hit Washington's RFK Stadium during a concert. Scott Shirley was grazed by it.
There was a very intense heat on the top of my head, and it was only on the top area. There was nothing on the sides or back, and it felt like my head was on fire.
The same strike nearly killed Lisa Sullivan. She's recovering now, but was burned over 20% of her body. She had no pulse, wasn't breathing, and her heart actually stopped beating for 7 minutes. A lightning strike may carry up to 200,000 amps of electricity, 1,000 times more than home wiring can handle. It can sometimes heat air around it to 50,000 degrees, hotter than the surface of the sun. But in a plane, you're probably safe. Lightning seems to bounce off. 150 a year are hit, but even minor damage is rare.
On the ground, your chances of being struck are only 1 in 600,000. But in a thunderstorm, don't take chances. Your best protection is to get inside a building or inside a car. But if you are caught outside alone, stay away from water, stay away from high ground, stay away from tall trees. Get down low, make yourself small, but without lying on the ground.
Harold Deal was struck years ago.
Threw me 50 feet, blew my boots off of me, left 2 holes in the ground where I was standing at the time I was struck, and I had $1.50 in my pocket. It melted.
Today, Deal can sit in snow without feeling cold, has no sense of temperature, taste, or smell. Is glad to have survived.
They never found me until the next morning.
As for those fires in Florida, no surprise lightning keeps setting more. Florida has more strikes than any place else in the nation. Bad news anytime. Worse now for the fires that won't quit. Robert Hager, NBC News, Washington.
Okay, so a couple of things here.
16 million strikes a year in the U.S., setting 1,500 fires, burning over 200,000
This one is interesting.
acres, destroying homes.
On the sides or
They carry up to 50,000 degrees, hotter than the surface of the sun.
Alone.
So how does anyone survive this? That's the weird thing that we need to focus on. I mean,
Stay away from water, stay away from high ground, stay away from tall trees.
Okay,
Get down.
forget about the electricity, the heat alone, whatever, just it should be enough to fry you. Yeah, people do survive something like that. All right, so a couple of things that people advise. Let's focus on this one.
Low. Make yourself small,
Okay, so you need to make yourself small, but
but without lying on the ground.
you shouldn't be lying down on the ground. Why not? That's something that we need to discuss. And when you get down on the ground, notice what he does with his body. All right. The best thing to do is make sure that your arms are touching your knees or below the knees for whatever reason. Something that we need to discuss next week, or next week.
But without lying on the ground.
Harold Deal was struck years ago.
Through me.
All right, so that's the only thing that I needed to talk
Bob and
about.
I are here to tell you about something that has us very excited. NEC's Parabola range of televisions. They've got a 3-year warranty, which we think is fantastic. They come from the same people who have sold over 1 million Australian-made colour televisions. Superb sound comes from the surround sound speaker system.
Okay, so what do we know so far regarding this commercial? Okay, Zach, you give yourself 10 points. That's absolutely correct. So the question is how? Okay, so it's a commercial coming from Australia. And obviously they're trying to sell you color television. That's not true. They're trying to sell you, this is from 20 years ago. They're trying to sell you high definition color TV. Okay, they're not the most interesting presentation. And obviously watching these guys will not make you go out and get one. So you can actually watch these guys trying to sell you a TV, right? It's not the most exciting commercial, and not like the commercials in the United States.
But the best feature of NEC's Parabola is its lifelike picture.
All of a sudden, the quality of this commercial goes from 0 to 100.
Bob and I are here to tell you.
You didn't even notice that the guy in the background was on TV. It's on a TV screen. You can't really, the quality of the image is so great that you can't really distinguish it from reality. So this is your high definition TV. This guy's going to be as boring as possible. This guy's going to try to look as bored as possible. And then next thing you know, it's just going to turn it off. And they, oh, I didn't see that coming. This was awesome. Okay. So high definition TVs, every single person has one today. That's the only sort of TV you can have. I got news for you. Like 25 years ago, like I say 20 years, this is 1996. So it's like 25 years ago. There was no such thing. There was absolutely no such thing. All right. So I got hired by an art school at the time to teach physics to art students. It was more of a trial basis. They weren't sure if they wanted to teach. Hey, stop. Hey. They were trying to make a decision whether or not they wanted to teach physics to art students. And if they did, they were looking for some real visual, some real conceptual, slightly mathematical base, which was going to make it worth for art students to pay 10 times more than taking a physics course at a community college. Okay, so they were looking for someone who could teach a course like that. And I was fresh out of graduate school. I took a leave of absence because I was working on my dissertation. And then I decided that, hey, on the side, let me just teach a little bit, make money. Okay, so I moved to Chicago. Chicago is one of the most expensive cities in the United States. And so they said, okay, so they were giving me $30,000 a year to teach physics at an art school, and the future of this course depended upon whether or not the art students were gonna like physics, basically. Okay, so I had no experience in teaching, except at graduate school, they let you teach labs, and I had my own tutoring business or whatever. So they were looking for someone who could teach visually, someone who could make it interesting, blah, blah, blah. I figured that I could do it in theory, because if you've never done it before, you think you can do everything because you're young, I only realized that this is not that easy. I had to get myself a cable, and then I started recording anything and everything I thought would be related to physics. So back then, we used to record things using a VCR, video recorder, in essence. And then I had the VHS tapes, which are like 6 hours long per tape. And I had 300, 400, 500 of them over the years. And then every single night, I would spend about an hour just going through a documentary. And per VHS tape, which is 6 hours long, if you're lucky, you could find something which was about 30 seconds long. TV back then was just full of trash. In the name of science, there was no science being done. And then the technology was just almost the editing technology, video editing technology, digital video editing technology, non-existent. All right, if I do the best technology software available at the time, I could do only 30-second digital videos, 30 seconds long. So needless to say, I'm spending maybe about 60, 70, 80 hours a week trying to come up with something visual, and nothing was working. It was just crap. All right, students kind of like me, but the course it wasn't working out. I was wasting a lot of time trying to prepare these lectures. It was trial and error, most of the error. We weren't going anywhere. I wasn't making enough money. I didn't have enough time to work on my dissertation. So I'm thinking, okay, it's time to get out. This is stupid. Time to get out. Let's go get a real job in physics, work in research, make money, and move on with my life. All right, so I started looking for a job in physics. And then, sure enough, I got lucky. This company called Zenith was looking for a physicist, and I was looking for a job, research position. Okay, so Zenith was one of the biggest companies at the time, 25 years ago, in the United States, comparable to Microsoft. Chicago-based company. They used to make TVs, and then they used to make computer monitors. So they're looking for a physicist. I'm looking for a job. I applied. They were interested, so I showed up for an interview. The first interview is at the HR's office. So they go through the benefits, the salary, blah, 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 blah. Starting salary was $120,000 a year. That's like 4 times the money that I was making at the time. And then I'm thinking, okay, this is good. It's 40 hours a week, 4 times the money that I was making at the art school. It's perfect. And it'll give me plenty of time to work on my dissertation. Okay, straightforward, what I need to do. Okay, so I was sold. Just give me the job. I'll take care of the rest. And then the HR said, well, just go to the physics department. They'll explain it to you. So that's the second stage of the interview. Now, this is a huge company. I figured that they had a physics department, which is about 20, 30 researchers. So I went down to the interview room. It's a small room. There's a small desk. There's a guy sitting across the desk. So obviously there was a chair in front of him. So I sat on the chair. So we started talking. And so he introduced himself. I introduced myself. He had my resume in front of him. And then, so we were going blah, blah, blah. And then the first question he had was, how much do you know about HD TV? Never heard of it. There's no such thing as HD TV 25 years ago. Right? There's no such thing. I figured that TV is TV. I didn't want to look really dumb. I said, given that TV is television, I said, what does HD stand for? This is high definition. Like, that really helped. I said, what does it mean? It says, just imagine that you're watching football in real life. Okay, how much of the grass can you see in reality? In reality, guys, you can't see the individual strands of grass. He said the image quality of this TV is just so great. It's digital. You will be able to see the individual grass on the screen. And I thought he was kidding. And now I'm thinking he's not. You can actually see that kind of detail. The stuff that you cannot see in real life. You can see it on the TV screen. It's amazing. And I thought to myself, wow, that's a good idea. That's an interesting idea. And then his next question is, do you know how a TV works? Jokingly, I said, just give me a remote control. I'll show you how it works. Not a big deal. He said, no, do you know the physics of it? I said, not only do I know the physics of it, I could actually build one if I wanted to from scratch. Because I was working on my master's in electrical engineering before switching back to physics. It's a piece of cake. He said, oh, okay. He said, that's fine. He said, we don't need you as an engineer. We need you as a physicist because we have a slight problem. I said, okay, so what is the problem? So he starts describing it. The problem is related to, he said, the electron gun. All right, so the engineers are cowboys, evidently. The electron gun is something that we refer to as a capacitor in physics. It's called the electron gun because it shoots electrons out of it. Okay, so within the capacitor or the electron gun, the way he was saying it. Okay, so one region is going to be negatively charged. So here's your negatively charged plate, and here's your positively charged plate. In the positively charged plate, there's a hole right in the middle. Attached to the negatively charged plate, you got this filament, all right? The metal filament, the wire. You heat it up to an extent that the electrons become liberated. So which means that you're ionizing the wire in essence. And this is happening under a very strong electric field. So what's going to happen is the electric field is pointing in the upward direction. So the electric field pointing in the upward direction, I'm hoping that I'm going to show it. Okay, so I'm showing it. Is going to induce a force on these charges, and these charges will accelerate towards this hole in the metal, and they will be shot out of the hole. That's the reason why the engineers refer to this capacitor as an electron. And then the electron beam exits the hole in this direction into a region where you have electromagnets, and the electromagnets will take this electron beam and trace it onto the screen a couple hundred times per second for the cathode ray tube TVs. Now for the high definition TVs that they were building, it's a few thousand times per second. Okay, so they had working prototypes already, and they were about to go to the market with the working prototypes that they had, and they were not able to do so because of the simple problem that they were having. I said, "What's the simple problem that you guys are having?" He said, For whatever reason, they had these prototypes. Each prototype cost them about $10,000, and within a span of 6 months, within the electron gun with the capacitor, it would just generate a spark, and the spark would just fry the electrons. That's it. Spark inside the capacitor would just fry the electrons. I said, okay, so what do you want me to do about it? He said, fix it. I'm thinking, oh, that's it. So I'm going to be making $120,000 a year fixing this problem. And as I was listening to the guy, I already had a solution for it. This was the easy solution. It was a fix. I not only had one solution, I had 3 solutions. I kind of knew how to fix it immediately because this is classical physics. And just before I opened my mouth and said something real stupid, because I didn't have the job as yet, I just wanted to know how long they've been working on this problem. And then answer was 4 years. I said, great, how many people? He said, me and the other guy. And then I said, can I assume that you're not a physicist? Because the way he was describing it told me that he understood physics, but that's the way the vocabulary, the terminology, the explanations, is that he lacked sophistication in explanation. He was more of an engineer than a physicist. Engineers don't have the same knack or understanding. He said, no, he said he had a degree in electrical engineering, minor in physics. I said about the other guy. The other guy was a physicist, had a master's degree in physics. I said, okay, so what you guys do? The first 2 years, he said, blah, blah, blah. He just listed everything that they did. The first 3 things that he listed are the things that I was already thinking about, and that stuff didn't work. Okay, good thing I didn't say it. Okay, so that the 3 things that I was thinking were the most obvious 3 things. They didn't work. And then, so the first year, they tried the 3 things, those 3 things. The second year, they came up with stuff which is a lot more sophisticated. I'm listening to him talk. I'm thinking, wow, this is genius. Yeah, I was drooling. This is. They came up with these weird ways of trying to solve this problem, and they came up with 6, 7 different things, and all of them are completely illogical, and none of them. So that's the first 2 years. And then the third year, they start using these advanced statistical methods. As soon as I heard that, I kind of remember rolling my eyes because I'm thinking this has nothing to do with this problem. I was slightly puzzled. I said, who came up with that idea? Oh, the other guy did. I said, how well did that work? As if I didn't know the answer. He said, it didn't work. And now what you guys do the 4th year? Oh, we applied more statistical methods, much more advanced than the previous years. I'm thinking, oh my God, this is like, it's nonsense. There's nothing to do with these advanced statistical methods, but I don't want to say anything because I don't want to offend anyone. I said, did that work? He said, no, that stuff was complete garbage. It didn't work either. I said, so what happened to the other guy? He quit. That's the reason why the job is available. He quit because he started applying all these advanced statistical methods. He just loved statistics so much that he decided to get his PhD in probability theory. I'm thinking, oh, so that makes sense. So this guy knew there was no way to solve this problem, and he knew that there was a certain time limit. These guys are not going to spend a lot more time trying to go to the market. They're not able to solve this problem. The guy quits and he goes, okay, I'm going to do a PhD in something else, and then just leave. And all of a sudden, the job is available. I'm there, and I'm looking at it, and I know that they tried anything and everything related to physics, and there is a solution to this problem, but the solution is not related to physics 100%. It's related to a branch of solid-state physics. Modern name of it is material science. Right? It's a hybrid between physics and chemistry, and it was just starting out at the time. I had people who were actually getting their PhDs in it because you need something that can hold on to these electrons under extremely strong electric field. I could see that there's no other solution for it that I can think of. And that's not my field. That's not, there are people who do PhDs in that sort of stuff. You can't just pull a guy from an art school and say, solve this problem, right? Because my background is in nuclear physics. My research is in nuclear physics. This is material science. It's not even related to physics. And the guy I'm talking to is an engineer. He wouldn't understand it. The other guy probably understood it well enough to know that, hey, you won't be able to solve it the way the stuff that they were using. So he decided to spend his time trying to get good at something that he wanted to specialize into. And all of a sudden he quits, the job is available. I'm looking at it, and I'm thinking, oh, I need the job, but I'm not sure if this is gonna work. So my first thought is, what else do you have? Because, yeah, I mean, if this is what they want me to solve, it's not a physics thing at this point. I said, what else do you guys have? I said, just don't worry about something else. We'll find you something else, just work on this. I said, I have to think about it. It's weird. As soon as I said I have to think about it, it's all of a sudden this guy gets slightly nervous because I don't know how many people they interviewed at that point. Evidently, there's no takers. I think a lot of people are going through the same process. They're going, no, this is not for me. They're just moving on. And he goes, wait a minute. He said, you know, you can publish this in high voltage magazines, right? I said, yeah, that's fine. I can see that. But I said, I still have to think about it. And then he goes, you know, is it because of the money? We can pay you more. I'm thinking, yeah. I said, I have to think about it because, you know, I didn't want to tell him exactly what I'm thinking because I don't see this as a physics problem. This is more of a material science problem. And then he said, okay. So thought about it for a few days. I called up the human resources department. I say, listen, from my vantage point, I said, these are the things that they could have done, and they've done anything and everything possible to solve this problem using physics. I said, I don't see this as a physics problem. I see this as a material science problem. So I said, on that basis, I'm just not going to take the job. So she thanked me. For a couple of days later, she calls me back. She said, oh, well, thank you for your advice. Based on my advice, she said they shut down the physics department and they moved the operations to Korea. I made no suggestions or recommendations. I just said, boom. Anyway, so they moved everything to Korea. That kind of made sense because I think it's cheaper. I mean, the quality of science is just as good. Material scientists, physicists, or whatever. They already spent 4 years of research money on it. Nothing was happening in the United States. They sent it to Korea. I don't know what happened in Korea. They were not able to solve this problem. So Zenith was the only company who was not able to solve this problem. Other companies were able to come up with their high definition TVs. They broke into the market. Zenith was a latecomer. It didn't work out. And then it didn't work out for them. I went back to the art school and things worked out for me, but not for Zenith, obviously. I figured out a way to teach these courses. All right, so the question is, how did I know that this was not a physics problem? The reason why I knew that, kind of dumb, the reason is because the sort of problem that these people were trying to solve using physics is exactly the same sort of problem that we don't know how to solve when it comes to lightning, okay? Lightning has the same sort of problem that this little spark that they were generating inside the capacitor does. Except inside the capacitor, the interesting thing is electric field is uniform inside the capacitor. And the biggest problem that these people were having at the time is the strength of the electric field was extremely strong, which means that they had a huge voltage difference between these two plates. Okay, so remember the guy said you can publish this in extreme high voltage magazines. So the question is, what is voltage? High voltage means extremely strong electric field. Stronger the electric field is, the faster the charges are going to move in this direction. As a result, you can take the electron beam and then trace it onto a screen a few thousand times per second, and then the quality of the image is going to be much sharper. I get that. But the problem with that is when the electric field becomes really stronger, and I'm not entirely sure how this was happening. To this day, I don't know. It starts to pull charges from the negative charge plate, and it's causing some kind of a spark on the inside. Okay, to this day, I don't know how that's happened, but you could tell that that's what's happening. When the strength of the electric field became really, really stronger, somehow these charges became energized enough to jump between these two plates. It was generating a spark. So the question is, where does this spark come from? Okay, so at least I have an idea of where the spark is coming from in this case. So he's charging up his body through friction. Okay, so his body is negatively charged. This guy is neutral. So what's happening is his skin becomes polarized. And at some point, this spark is going to happen, which means that there's going to be an electrical discharge. Okay, so one thing that I want you to notice about the spark, though, happens only at a given distance. All right, this distance about an inch or less than an inch. All right, it's an inch or it's less than an inch. I think you would have figured out, Mr. Zenith. No, I gotta tell you, Zach, it's just, I'm still mystified. I kind of have an idea still, but I don't exactly know what's causing the electrons to jump out of that metal piece. But here is straightforward. But the distance matters here, right? So at a given distance, literally, there's going to be a discharge, which means that it's going to pull positive charges from the skin, and then the negative charges get pulled out of his finger, and there's an electrical discharge. The distance is going to matter. So why is that this happens at a given distance? Why not like 10 feet? Why not half an inch? Why do we get to start happening at that distance? All right, so it's going to be related to the electric potential or potential difference. All right, you guys are technology majors, so the terminology is important here. Not the math, but the terminology. Okay, so the V represents the voltage or potential difference. If you don't get this right away, don't worry about it. I'll explain slightly differently. So it will make sense at some point. This is a really abstract concept. voltage or potential difference depends on the strength of the electric field between the separation distance between two opposite charge regions. It depends on the separation distance between two opposite charge regions. Whoa. Okay, let me just back up out of this. At first, let me just give you the meaning of the formula. All right, so positive charge region, the negative charge region. Electric field is pointing in this direction. The strength of the electric field times the separation distance between these two opposite charge regions is known as voltage or potential difference. Okay, so that's what it is. But what does it mean? The voltage or potential difference represents the amount of energy stored within this region inside the electric field. Okay, so it represents the amount of energy stored within the electric field within that region. All right, so V is the voltage, or we say voltage difference. Instead of saying voltage difference, we say voltage. Okay, you will hear that a million times. You guys are technology majors. When somebody says voltage, high voltage, blah, 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 which means that that region has, if somebody says high voltage, which means there's a live electric field within that region, and you don't want to be in this region. You don't want to put a wire in this region. You don't want, because as soon as you place something here, the charges will move across it. That's what it means, because which means that the electric field is going to drive the charges through that material. So it's an energized region. That's what it means. All right. So the energy is going to be inside the electric field. It's going to be stored inside the electric field. And then how much energy is stored depends on the separation distance between these two regions. Okay. So voltage difference or voltage represents the amount of energy stored in the electric field between two opposite charge regions. All right. So here's the voltage is going to be expressed in terms of voltage difference or whatever, or potential difference. They mean the same thing. So it's going to be expressed in terms of voltage. Use the electric field. R is the separation distance between these two opposite charge regions. Okay, so what else do we have that we need to talk about? All right, so this yellow region is energized. That's what it means. So within this yellow region, you got energy stored within the field itself. Okay, so now if you were to drop a charge into this region, like a negative or positive charge, this charge will become energized. That's what it means. So which means that stronger the electric field is, more energy is going to be stored in it. And when I place a charge on it, okay, so let's think about what happens. Okay, this should make perfect sense to you right now. What's going to happen is electric field is going to act on this charge, right? Inducing a force on it. As a result, this charge is going to accelerate in the downward direction. That's what happens. So the charge is going to speed up. Stronger the electric field is, the faster the charge is moving. Okay, so that's what he was saying. High voltage magazines, which means that the electric field is so strong within this region that the charges are moving at extremely high speeds, so you can trace them onto the screen to create a better image quality. Okay, that's one way of saying it, but there's a second way of saying it that we will focus on. So the energy is stored within this region. So if I place a charge, what happens is now the charge becomes energized. Okay, now the charge is potential energy. Right? Okay, so potential energy is the stored energy. When you lift something up, you energize it. When you let it go, what happens? That energy turns into kinetic energy, right? Same thing happens to the charges. Okay, so energy is stored within this region. When you actually place a charge in that region, immediately the charge will become energized, and that's your potential energy. If this charge is free to move, that potential energy turns into kinetic energy. So immediately potential energy goes down, the kinetic energy goes up. Because electrostatic force is a conservative force, just like gravity. Okay, so we use potential energy, PE and U, they mean the same thing. All right, so which means that now I have the voltage or potential difference within this region, which means that the energy is stored within this region. If I put a charge into this region, now it becomes energized, and that's the potential energy. And this potential energy, if this charge is free to move, is going to go down, and it's going to get converted to kinetic energy. So bigger the potential difference is, larger the potential energy is, the larger the kinetic energy becomes. So the faster the charge is on. Okay, so because remember, mechanical energy is a combination of kinetic and potential energies. Okay, this E and that E are not the same. This is mechanical energy. So I'm just going to put down N. I don't know why N, and E is energy in this case. En is the energy. All right. So mechanical energy is a combination of kinetic and potential energies. Mechanical energy is constant when there's a conservative force field. Electrostatic force is a conservative force field. So what I'm saying is the potential energy of this charge, if the charge is free to move, is going to turn into kinetic energy. All right. So larger the potential energy, larger the voltage is, bigger the potential energy is, the faster the charges are moving, in essence. Okay, that's it. All right. So all this blah, blah, blah means high voltage means a very strong electric field. So that if you have charges in anything, the charges will become energized, and these charges will start to move in the direction or in the opposite direction of the electric field, generating currents. So if it says high voltage, don't step in it, because you got charges in your body. The charges are free to move. So which means that there's going to be a tremendous amount of current going through your body. That's what it means. Okay, so you guys are technology managers, just understand it. I'm just giving you the physics. All right, so large voltage difference means an extremely strong electric field. Electric field acting on these particles will cause them to accelerate When you place a charge into a field of potential, they have potential energy, which means that the energy is going to get transferred to the charges. If the charges are free to move, this potential energy is going to get converted into chemical energy. I said it wrong. This potential energy is going to get converted into kinetic energy, which means that they're going to be moving faster and faster. Okay, so that's the story. So that's what I was trying to get at. So strength of the electric field times the separation distance between two oppositely charged regions will give you the amount of energy stored within that region. And then when you place a charge within that region, it's got potential energy. If the charge is free to move, that potential energy is going to turn into kinetic energy. So these are the electrons exiting the hole inside the TV that you're looking at. Because of the potential difference, all of them will have the same amount of potential energy, so all of them are going to move at exactly the same speed as exiting this hole. And the motion becomes predictable. All right, this was fairly abstract, all right? And hopefully you got parts of it. Okay, so we should be able to get something out of this. So high ground is more dangerous than the low ground, so the question is why? Before I answer that question, just focus on this.
I wanted to show you that electricity can actually be useful. So when my young friend here told me that she wanted her hair teased, I thought maybe I would do it on this Van de Graaff machine. You know, this won't hurt a bit. There we go. Now watch what happens when I turn it on. You see that? Electricity can be absolutely hair-raising. She wanted to know how much this would cost, but I told her that by the time I was finished, there'd be no charge.
Somebody has a really deep understanding of physics and enjoyed the joke better than most of them did. All right, so this is from Caltech. Okay, so one of the things that hopefully you guys notice is just before the lightning strikes, okay, this is one of the things that you will see. All right, so your body becomes polarized and the hair becomes polarized. So in this case, the hair is either positive or negative charge. Like charges will repel, so your hair is going to rise up. All right, so this is one of the signs that this person is about to be struck by lightning. Okay, so that's one of the things. So the question is high ground versus the low ground. Which one is going to be more likely to be struck by lightning? Okay, let's go through the physics of it. So the bottom of the cloud is negatively charged. The ground will become polarized to become positively charged. Initially, it's negatively charged, so it's going to become positively charged. So the step leaders coming from the clouds, and then the streamers are going up, positive charges are going up. High concentrations, when they meet up, you got the lightning. Very good. All right, so separation distance, I'm just going to make up some stuff. The distance between the clouds and the ground versus the clouds, high ground versus the low ground. Okay, so let me make this about a football field in length, 100 meters, 100 yards. I'll make this 10 times a football field, 1,000 yards, 1,000 meters. Okay, let's get an idea. Now, whenever the strength of the electric field reaches this value, 10,000 newtons per coulomb, the lightning usually strikes. So the high ground to clouds, 100 meters, low ground to clouds, it's going to be 1,000 meters. Let's take a look at the potential difference for these cases. So the voltage potential difference is strength of the electric field times the separation distance. So high ground in the clouds is going to be 100,000 volts. Low ground in the clouds is going to be 1,000,000 volts, I think. Oh, no, this is 1,000,000 volts. Am I missing something? 1, 2, 3, 4, 5, 6. Okay. High ground and the clouds, 1,000,000 volts. This is 10,000,000 volts. Okay. This makes sense. Okay. Okay, so the voltage difference between the high ground and the clouds, 1,000,000 volts. Low ground and the clouds is going to be 10,000,000 volts. Okay, so based upon this information, I will conclude that it's more than likely that high ground is going to get struck first. Okay, so how did I arrive at that conclusion? I was able to arrive at that conclusion based upon my understanding of voltage and potential. Right? In this case, the voltage and potential represents the amount of energy required per charge for these charges to jump that gap. Okay, so the voltage and potential, that's the potential energy stored inside the electric field. So the voltage and potential represents the amount of energy required per charge to jump that gap. All right, so the amount of energy required per charge to jump the gap between the clouds and the high ground is going to be a 1,000,000 joules of energy per coulomb of charge versus jumping the gap between the high ground, the low ground, and the clouds. It's going to be 10,000,000 joules of energy per coulomb of charge. So which means that the charges in the cloud will require 1,000,000 joules of energy per coulomb of charge, which is known as voltage. So they will require 1,000,000 volts of energy before they require 10,000,000 volts of energy. So which means that they will require enough energy to jump the gap, the smaller gap, than the larger gap. That's the reason why they should be striking the high ground. But if this logic is so correct, they should be striking the high ground 100% of the time. All right. yet only about 70 or 80% of the time, not 70% of the time, maybe close to 70% of the time, it's going to strike high ground. And 30% of the time, it strikes low ground. I mean, if physics is so accurate, if that explanation that I just provided is the correct explanation, then 100% of the time, the lightning should strike high ground. Yet only strikes high ground maybe about 70% of the time. Okay, why is that? So which means that there is more to the story than we understand. Okay, so that's one of the things that these people at ZNet was trying to solve, is we're understanding of this phenomenon is they didn't understand that we're understanding of phenomena of discharge is not 100% accurate. It's maybe about 70% accurate, 30% of the time, who knows what happens? Okay, so who knows what happens? Let me explain the stuff that we don't know. And then we'll try to provide an explanation as to what's happening 30% of the time. We don't understand what causes further separation of the charges, guys. That's an unknown. The ground becomes positive charge. This is polarization, but there are positive ions coming out of the ground. We don't know where these ions are coming from either. Okay, we don't have a really good understanding of this stuff either. And on top of that, things happen during the lightning phenomenon. Kind of random.
One of the most surprising discoveries is that lightning is blind as it streaks towards the Earth. It is only in about the last 100 feet that it senses the Earth's electromagnetic field and selects a place to strike.
When it does come down, you can see in this picture here that it's coming in little 50-yard steps, 50-meter-long steps called step leaders. It keeps coming down toward the ground. In this part of the channel, this is the one that made it to ground. As it comes closer to the ground, when it gets down to this last little part here, this is the really important part. This last 30 to 50 yards, it looks for something to hit just in this little area.
As the step leader streaks towards the Earth, anything sticking up, buildings, trees, even people, send up positive streamers in response. When they connect, lightning is born. Negative electrons are discharged to Earth, and a positive charge travels back up the cloud at 60,000 miles a second. Here, two streamers leave the tree, but only one successfully connects with the stepped leader. The telephone pole has also launched a streamer, a failed lightning bolt. Packing up to 100 million volts of electricity, lightning has the power to explode walls of concrete and destroy electrical systems. Each bolt is 5 times hotter than the surface of the sun. Exposure to its power for a fraction of a second can be lethal. It was a beautiful afternoon in Colorado, and hundreds of people were out soaking up the summer sunshine. But out of the clear blue sky, nature played a cruel trick.
It happened on a day when there wasn't a cloud in the sky. It was a clear blue sky when, from out of the blue, a bicyclist was struck by lightning. It seemed mysterious to us because where was the cloud from which this lightning originated? This was the first opportunity we thought we had to investigate it, to find out where that cloud was. And to do that, we sought the help of Global Atmospherics in Tucson.
But would Global's system be sensitive enough to pinpoint this mysterious bolt?
We went back and plotted the data for the 3-hour period around the time when this event happened in Vail. If we look here at the screen, we can see the flash over Colorado, and in this case, there was only one flash within 20 miles of this particular location in Vail. This is definitely the one that struck the person.
They found that the single lightning strike in this county at that time of day, on that day, originated in a cloud 10 miles on the other side of this mountain. That cloud was not visible in the valley, so there was no reason for the people, including our patient, to seek shelter. But it is not unknown for lightning to travel some distance, including, in this case, 10 miles, in other instances even more, before it takes a downward dip to reach the ground.
They may appear to come out of the blue, but they are coming out of a thunderstorm for reasons we don't understand. The lightning sometimes will come out sideways from the cloud rather than down below it.
Lightning is capricious. Lightning, which is a beautiful phenomenon of nature, and we all can sit and watch it, but it also can be one of the most cruel phenomena of nature. And this one was particularly cruel because it was hidden.
Lightning is among the biggest natural hazards, killing more people each year in the U.S. than hurricanes, tornadoes, and earthquakes. The paramedics in Lightning Alley are only too aware of this. This storm has already claimed its first victim. Who will be next?
Actually, lightning generates tremendous amounts of heat, and with that comes instant water vaporization, which, with like clothing, results in an explosive appearance of the clothing. It becomes shredded, metallic objects become fused, such as zippers. And surprisingly, with all this heat that's being generated, there are relatively few burns and some singeing of hair. What we also know now is that there's a tremendous amount of explosive effect or mechanical effect of the lightning that will cause eardrums to rupture, it can cause bruising of the heart, and contusions of the brain, as well as some skull fractures.
With this sort of power, it's surprising that anyone survives. It's a hot, humid summer's day. Thousands of people are gathered at RFK Stadium for the Freedom for Tibet concert. Suddenly, disaster strikes. One young woman has been singled out from the crowd by a lightning bolt, stopping her heart and paralyzing her lungs. 3 years later, the victim has made a remarkable recovery.
My sister Amanda and I were sitting around here when we came to the concert, and it was a nice day in Washington, which is unusual in June. It was sunny and not too hot, and we were watching the show, and all of a sudden, a huge cloud came out of nowhere without any rain, and a bolt of lightning came out from the sky and hit me right on my head. I was thrown onto the ground, and 2 people near me in the crowd rushed over.
Luckily, one of those people was an off-duty doctor.
She was bleeding from her lips at the time, so we wiped the blood off of her lips, and we started CPR right then. And we also started chest compressions at the same time because she didn't have a heart rate. And it was about 10 minutes after I initially seen her that she regained a heart rate of her own. Without the CPR, she probably would have been brain dead.
Lisa had taken a direct hit from the lightning. As she was rushed off in the ambulance, the medics didn't know if she would survive. But why had Lisa been selected from a crowd of over 66,000 people? She wasn't the tallest object. There was the top of the stadium. Even the musicians on the elevated stage would have been an easier target. A discovery made 60 years ago may hold the key to Lisa's mysterious attack. Throughout the 1930s and 40s, the General Electric Company studied the way lightning bolts hit the Empire State Building in New York. They found that the Empire State was hit on average about 23 times a year. But when the team went back and analyzed it, it appears that sometimes a lightning bolt is too weak. It appears that sometimes a lightning bolt is too weak to trigger a streamer until it gets much closer to the ground. By this time, it may have already missed the tallest object.
This makes it possible for a leader, if it's very weak, doesn't have much charge in it, to propagate down towards the ground parallel to, say, a tall building like the Empire State Building. And if it always stays 50 or 60 meters away, it can come all the way down near the bottom before a leader comes off the side of the building at some random point and meets it, and then the lightning attaches to the side of the building. So the tallest thing around is not always what gets hit. Leaders without much charge on them can work their way in between buildings, or can hit the bottoms of trees, or can do things that you wouldn't think otherwise would occur.
The bolt that struck Lisa may have sent down a weak-stepped leader, which sneaked past the top of the stadium and the stage. Other people in the audience, as well as Lisa, would have sent up streamers to try and trigger the lightning bolt, but as it zigzagged closer and closer to the crowd, it was only Lisa's streamer that made the fateful connection. As the lightning flashed over Lisa, the searing heat caused second and third degree burns over 20% of her body.
These are the clothes I was wearing when I was hit by lightning. My mom kept them so I'd understand the sheer force of what I survived. The shirt, you can see, was just totally blown away. And my bra, which had a metal underwire, was melted, the metal, and it caused a third-degree burn under my one breast. Something I never understood, though, was how this could have happened if I was wearing 2-inch thick rubber sneakers. I even asked the doctors in the hospital when I realized what happened to me. I later learned that sneakers aren't going to save you if there's a lightning bolt anywhere near you.
Lightning hits the Earth 100 times a second. In the U.S. alone, there are more than 25 million cloud-to-ground strikes each year. About 1,200 of these will hit people, and 100 will be fatal. The reason why so many people are struck each year is that our fluid-filled bodies provide excellent pathways for electrical charge.
The thing about the body is that it's a very good conductor of electricity. Most of the fluids in the body are very salty, and so they conduct very well indeed. And I can show you that on this ball here. These little streamers are just like lightning, except they're very, very small in the way of current. And you can see just how concentrated the electricity becomes. And if I put my whole hand, you can see how most of the streamers concentrate around the hand. And it's being conducted down my arm and through my body and away to Earth. Now, perhaps I can make that a little plainer by using this fluorescent tube, and I can conduct current through the fluorescent tube. If I put the tube like so, you can see current is being transferred through here, along through my right arm, and down and away to Earth. If I do it on this side, the same happens but on the other half of the body.
The same property that allows us to conduct electricity from the plasma ball also makes us living lightning rods. 3 years later, Lisa is back to normal.
When I feel like I'm taking life for granted, I take a step back and I go, you're extremely lucky, because there's a huge chance that you wouldn't have been here, so enjoy today.
Lisa was very lucky. Only a small number of people who suffer a direct hit from a lightning strike live to tell the truth.
Actually, lightning just...
Okay, so there are a couple of things here. Bunch of explanations.
Thrown onto the ground. Huge
disaster strikes.
And we start actually
1,000 people.
Skull fractures.
It was nice to have on
Brain dead.
Okay, so majority of people usually survive, but not too many people survive a direct hit. A lot of them are side flashes.
Object.
This makes it possible for
Trigger a streamer until it gets much closer to the ground. By this time, it may have already
So there's a certain degree of randomness involved.
missed the tallest object.
this makes it possible for a leader.
Try and trigger the light.
Okay, so we send out these streamers. These are positive ions from our body. And if there's a connection between the step leaders and the streamers, that's when you get struck.
But as it zigzagged closer and closer to the crowd, it was only
And her streamers made connections, so she got struck. She was talking, she didn't quite understand. She was wearing sneakers and all that stuff. Number one, she's sitting on the ground. Unless you got a rubber ass, of course, you're gonna get struck. But forget that. Even if you had a rubber butt, it makes no difference. Your body becomes polarized. Okay, so you will get struck. One of the things that this guy demonstration that he was doing that I really like is, if you want to know whether or not you're about to be struck by lightning, is you need to get these fluorescent bulbs, and then you can just carry it around if you're that suspicious. If it lights up, which means that you have about a minute. Okay, so you don't need to even be touching anything. He wasn't touching anything initially. So if you just energize this is just gonna light up, which means that if you got streamers, if you're sending out streamers, if the step leaders are connecting with it, you're about to be struck by lightning. You can get a pocket size if your crutch lights up, which means that you're about to be struck by lightning. Or they have, it's specially designed ones that you can buy on the net, it's gonna cause a vibration. All right, so that means that you got a minute to do something about it. The best thing to do is just get into your car, and that's the end of it. All right, I wouldn't recommend that you stick around.
overcoming the damaging effects of one lightning
Now, most people do survive, and a lot of what they survive is
strike can be hard enough. But a few rare individuals, like Park Ranger Roy Sullivan, are proof that lightning can strike twice and more. His daughter remembers his first strike.
This is from the first one. That's in 42, and lightning went through his watch. You can see it has a hole through side to side.
For 27 years after this first strike, Roy was untroubled by lightning until one fateful day in 1969. A side flash bounced into his truck, hitting him in the neck and burning his head.
All right, so let's stop at this point and let's analyze this one. He's inside a vehicle. He's still getting struck by lightning. Also, right, like an hour ago, I said this is impossible. It would never happen. You're inside a vehicle. It's a metallic enclosure. That's a Faraday's cage. While that's true, I was talking about a direct strike. You're not going to have a direct strike. Usually, the side flash can still happen. So the only way to avoid getting struck by lightning is make sure that the window is up, all the way up. All right, so which means that the connection between the streamers from your body and the step leaders from the ground is completely separate. All right, just don't leave a gap. Just roll it up all the way up, or else you can get struck by a side flash. Most people get struck by side flashes, and they do survive.
The odds against Roy being struck a third time were over 1,000,000,000 to 1. But only a year later, near his home, lightning hit a transformer and arced to his left shoulder. But this was not the end. In 1972, while taking refuge from a storm inside a mountain station, Roy Sullivan was singled out for a fourth time.
I recall Roy having lost all of his hair on his head. He also had a burn around his ankle that was, I would consider, substantial.
Morning, Rick. How are you, Roy? Pretty good. Working a lot today? Sure am. Have a good one. You too.
By 1973, Roy had taken to carrying a bucket of water with him when he made his rounds, in case he caught fire again. Even though he tried outrunning the thunderstorms, in June 1976, Roy was struck again for a record sixth time. And his troubles weren't over yet. The following year, while out fishing, Roy was struck for the seventh time, and he became known as the Human Lightning Rod.
People called him that before, human lightning conductor, but I don't know. I don't know if it was a chemical mineral in his body. He said that before.
Roy was worried that metal on his body might be attracting the lightning.
He didn't even wear a wedding ring or a watch because of that. He didn't wear those.
Belt buckles and metal zips fuse and melt after a lightning strike, and many lightning survivors have terrible burns from metal objects that they were holding or wearing. But does metal on the body actually attract lightning? At a high-voltage lab in Manchester, England, researchers are preparing to find out.
We use an impulse generator, which is charged to a voltage of approximately 1.5 million volts.
To see if it will
They simulate the resistance of the skin of a human under normal conditions.
Various metal objects have been attached to the
All right, so it's gonna be at the same height. She's the one who's wearing the jewelry. He's not. All right, so this is metal. I think she's got metal hair. She's got metal hair. So this dummy's not
test
wearing
dummy on the
anything.
left to see if it will be struck by lightning more times than the one on the right.
All right, so all 3 times she gets it. And finally, she gets struck. And look at his reaction. Not an impartial scientist at all. I have to assume that he's got some metal problems.
In this test, the dummy without metal was actually struck more often than the one with metal.
So what does it mean? That means that the metal on your body does not attract lightning.
Just like a real lightning strike, the electrical flashover has left telltale fractal patterns on the dummy's body. If Roy Sullivan did have any metal on his body, it should have had no effect. Lightning experts believe it was due to a combination of high exposure and bad luck.
Roy Sullivan was outdoors in an area with quite a bit of lightning. He was exposed to the lightning a great deal, more than most people are. A visitor is maybe there for a few hours or a day or so, but he was there for many years, and that cumulative effect catches up with him.
So the next question is, does the size of the metal matter in terms of attracting lightning?
Maybe even more metal. Of course, if your tongue piercing is this big, lightning is the least of your worries.
I saw it go into the top of the head and go out to the bolt and back in.
It just goes to show, don't put any really big bolts in your mouth during a thunderstorm.
Finally, a test for the mother of all studs.
Both cheek piercing there.
It's unlikely to catch on at many nightclubs, though it might just help you get in the door. Will it attract lightning? At last, a direct hit.
Well, that knocked the doorknob right out of his face.
Okay, so does the size of metal matter in terms of attracting lightning? Conclusion is straightforward if it's coming from Mythbusters. All right, so if Mythbusters were to be believed, of course the size is going to matter. That's the reason why they will say, don't put a doorknob on your face, right? So that you don't get struck by lightning. So as far as Mythbusters are concerned, of course, the size of metal is going to matter. Really? If that's the case, the cars should be the ones who are getting struck by lightning. The buses should be struck by lightning more often than the cars. The train should be struck by lightning more often than the buses. But that's not at all what we see in real life. Okay? The buildings are much bigger than the lightning rods. Why is it that the lightning rods are getting struck by lightning? Lightning rods will get struck by lightning more often than your car. So is it the metal that attracts lightning, or is it the shape of the metal that attracts lightning? It's not the size, it's the shape. Okay, so shape matters. Okay, so the metal itself is going to become polarized. So the Earth's surface is positive charge, so the metal is going to become positive charge. Charges will repel each other as far away from each other as possible. So depending upon the shape, the sharp edges and the pointy edges will have higher concentrations of charges. So charge density goes up. So what happens when the charge density goes up? The electric field becomes stronger and it becomes more attractive to the step leaders. Or so if there are any step leaders around, it's just going to grab the step leader. That's what it does. Okay, so it's the shape that matters. Notice that the lightning rods tend to be extremely long, extremely sharp, and extremely pointy. The reason why we use metal, because metal is a conductor, it becomes polarized extremely easily. Charges are free to move. And around the sharp edges, you will have extremely high concentration of charges, the positive charges. The bigger the concentration, higher the density, the stronger the electric field is, more attractive it becomes to these step leaders within that region. And step leaders will become attracted to this as opposed to building. That's the whole idea. And the lightning rod, through design, is going to take the charges to the ground, immediately bypassing the building. All right, so it's sharp, it's pointy, it's very smart. That's the design that Franklin came up with. And he did not patent it. He gave it to the world free of charge. And King George said, no, thank you. I came up with my own design. The design that King George came up with is a spherical design. All right? He said, no, we're not going to make it pointy. We're just going to make it spherical. How does that work? Not as well. Because you will have a uniform charge distribution. When the charge distribution is uniform, the electric field is not as strong. It's not as attractive to lightning. So why would the king in this case, the King George, would just snap what Franklin came up with and made it available free of charge to the world. Well, it's got everything to do with the reason why we got Franklin's picture on a $100 bill. Britain ended up losing colonies under King George. This guy could never forgive Franklin. And he thought that it was smart enough, not so much. All right. So what do? If we have a metal piece, a rod, I don't know, like the car's antenna, and if you don't want to get struck by lightning, what do? You put a small ball on it. Why do we do that? Because we know that that's one way to prevent the lightning from striking. So King George came up with a way to prevent a lightning striking a rod as a sword. And Franklin found a way to have the lightning strike a rod, which became the lightning rod. All right, so that's the difference. If you want to attract lightning, you need to have something which is long, sharp, as well as extremely pointy. If you want to prevent from getting struck by lightning, just get rid of those sharp edges. Make it more like a ball. All right. Germans are smart. World War I, German military helmet. By the way, guys, this is metal. It's not the metal that attracts lightning. It's the shape of it. A lightning storm, and they noticed that they were losing a bunch of troops. World War II, they decided that they were going to keep the helmet, and they got rid of the spike. Okay, so no spike. These were walking lightning rods. And speaking of the lightning rods, they noticed that the umbrellas changed quite a bit over the years. They used to be a lot more pointy, or pointier, I'm just going to say, than today's umbrellas.
In the middle of a children's soccer game, the skies open. Players take shelter under a tree, and the coach puts up a large umbrella. It's a
kind of like
terrible
this.
mistake.
Notice that immediately the umbrella starts to act like a lightning rod. This is a sci-fi, so the person's going to get struck.
17 people feel the force of the lightning strike. But how could so many have been hit by a single bolt? Most victims are not hit by lightning directly, but by a charge that jumps from a nearby object, such as a tree. This side flash still has enough power to stop the heart and burn the skin. Victims can also be shocked from below. Immediately after a strike, the ground becomes electrified.
Okay, so that's a second reason why most people do survive something like this, right? It's not a direct hit. You got the side flashes. On top of that, the ground becomes electrified. Here's the reason why you should never, ever lie down on the ground. Okay, so my recommendation is
the current travels through the person where they make contact with the ground.
Keep your legs together. Keep your feet together next to each other.
Usually up one leg and down the other.
If they're separated, there's going to be a voltage or potential difference between the legs, so which means the current is going to go up one leg, come down the other.
If you're caught out of doors in a thunderstorm, the best thing to do is get indoors in a sizable building. If you can't do that, you should get into a metal car.
The car's metal body discharges the current away from the driver and below.
Never stand under the tallest tree. Try to stay off hills where you're the tallest object.
But you're not totally safe indoors.
If you're indoors, you shouldn't touch anything that's connected to the outside because the lightning could...
I mean, this is kind of weird because he talks about the safest place to be. Is it indoors or the car? He just favored the indoors. And then now he's going to explain.
Strike that outside and come in. And that includes the telephones with wires. Shouldn't be leaning against the refrigerator.
He says indoors, sizable building, but now he's going to qualify it. He says, don't be touching anything which is connected to the outside. Like, don't be touching the fridge.
Shouldn't be near the house plumbing.
All right, so no pissing or crapping.
Shouldn't be in the shower.
Don't be in the shower. Don't be getting anything from the fridge.
Just stay away from everything.
Stay away from everything. Guys, versus inside your car. All right? You can do anything. You can do anything inside the car. You're still going to be there.
Amazingly, all 17 victims survived.
Okay, so it's just a minute long. All right, so we got 4 people, and all of them will survive. This was bad. Okay, this looks to me like a direct hit. Okay, let's keep watching it. Yeah, so okay, I assume that this is a slower one. Okay, so I think the tree got hit, and these people got hit because of it. And all of them survived. I don't think this is a direct hit. Some people do survive direct hits. It's not very common though. Okay, a majority of the people who get struck. Like this is an extreme case. I'm going to count this because all of them are under the tree and all of them were leaning against the tree, and they all got hit, and evidently all of them survived, with one being critical. So I don't see anything surprising here. This is a bad idea. You don't want to be under a tree like that. You don't want to be under anything tall, especially under a tree. All right, this was bad. I can also tell you that these people didn't feel a thing. This guy just was leaning, probably had a really good balance. Eventually, he just goes down. And he's still, these guys are unconscious. This guy's still moving his arms. Okay, Edward, give yourself 10 points for that one. That was actually interesting. I like it. Okay, so the one that we didn't really cover.
In Glenview, high winds took down a power line, trapping a woman inside her car.
Okay, now the electricity is outside of the vehicle, right? So this vehicle is part of the circuit at this point. All right, so this entire vehicle is electrified. She's touching the metal on the inside, so she's fine. I said she can also touch the metal outside. She's still going to be fine. Okay, so the question is why? The only thing you know is the net charge is going to be outside, which means that the current is going to be outside. The net charge is going to be outside. The electricity is going to be outside. That's the only thing that you know up to this point. Okay, what's so confusing about this is there's no electricity on the inside. There's no net charge on the inside. So she could touch the metal on the inside. You get that. But all of a sudden I say she can touch the metal outside. She's still fine. And all of a sudden your mind goes berserk because you don't understand that. Because you're thinking, wait a minute, I don't get it. Electricity is outside and this person is literally dipping her hand into the moving charges. Electricity means it's not static. There's a current, which means that there's current of charges. Charges are moving in the same direction. That's the second part of this lecture coming up. So it's not a static situation. There's a net flowing charge outside. So if you touch the outside, you were thinking, oh, this person is in big trouble. This person is going to get shocked. The answer to that question is no, nothing is going to happen to this person. Okay, so a couple of things that you know up to this point. Here's what you know. The net charge is going to be outside. And you know that the potential or voltage difference means that there's going to be a, okay, I'm going to find a way to explain this. Okay, so you got your hollow conductor. Okay, this could be your car or an airplane. Let's take a look at the potential difference between the surface and the inside of it. Okay, so if there's any sort of potential difference between the surface and inside of it, that's going to set up an electric field. And within that electric field, if you place some charges, if there's some free charges, the charges are going to move in along the direction of the electric field. Okay, positive charges will move in the direction of the electric field. The negative charges will move in the opposite direction of the electric field. So we'll check to see if there's any potential difference between the inside and the surface, between the inside of the hollow conductor and the surface of it. Given the fact that the net charge is going to be on the surface, what that means is the net electric field on the inside is going to be zero, because there's no electric field inside the hollow conductor, like a Faraday cage. Okay, so all the charges will be outside. The net charge is going to be outside. Because the net charge is outside, within a hollow conductor, there's absolutely no electric field. Okay, so the electric field inside is going to be zero. If there's no electric field inside a Faraday's cage, a metallic enclosure, the electric field is what forces the charges to go through your body. All right, so if there's no electric field inside, there's no potential difference between inside and the outside of the surface. All right, so if there's no potential difference between inside and outside of the surface, which means that there's no way the charges can be forced to go through your body. Okay, so you can literally touch the outside surface of a metallic container or enclosure without being shocked, because there's absolutely no potential difference between the inside of the enclosure and the outside of the enclosure. All right, if there's no potential difference, which means that there's no electric field that forces the charges to go through your body. As a result, you can touch the outside of the metal, you're perfectly fine. Okay, as long as you're inside the metal, as long as you're inside this metallic enclosure, that statement is correct. So there's not going to be any voltage or potential difference between inside and outside. If there's no potential or voltage difference, there's no electric field between inside and outside, which means that the charges cannot go through your body, because the charges have to be forced to go your body.
That's what I'm talking about. I will. I love you too. Whoa. Oh man. So that's what an airbag feels like. My car! Great. I should probably get out and see how bad the damage is. Wait. Are those telephone wires or power lines? Either way, they could be hot. No way to be sure. Don't take any chances. Just stay in the car and call 911. Good thing I actually paid attention during that safety meeting. Hi, this is Stephen Stonebanks. I've been in a car accident. I hit a power pole. I'm on Highway 18, somewhere east of the 356th Street exit, a couple of miles. No, I'm okay, but there are power lines on my car. Okay, yeah, I know. I won't move until you tell me that the line is de-energized. Yes, I will stay put. Okay, please hurry. Thank you. Honey? Listen. I've been in an accident. I'm fine. I hit a power pole. The car is a mess, but I'm okay. Yeah, I've called 911. They're on their way. Oh, no. Hey!
Are you okay?
Hey, stay back! No, don't come any closer. You could get shot by the ground around these down power lines. Stay back about 35 feet and make sure no one else comes near.
Okay.
I called 911. They're on their way. Thank you. Honey? No, I'm fine. No, don't worry. Yeah, the police are on their way. Yeah, all I've got to do now is sit and wait. Honey? I gotta call you back in a couple of minutes. Oh boy, not good.
Oh my gosh.
Okay. Plan B. Exit the vehicle. But now I gotta worry about touch potential. Touch potential is risk of electrocution based on one part of the body touching an energized object like a car while simultaneously touching the ground. Electricity flows from the vehicle through the body and into the ground, essentially making me into a human jumper cable, which would be bad. I gotta jump and land with both feet together. Whew! Okay, now, step potential. Because the ground is energized, electrical current can travel through me if my feet aren't close together. Electrical current enters through one foot and out the other. The further apart my feet are, the greater my chances of getting shocked. So I must move away using short, shuffling steps. Shuffle, shuffle, shuffle. There you go. You got this, Stephen. No large steps. Just keep on shuffling. Every day I'm shuffling. I'm sorry, I can't come to the phone right now. I'm busy trying to stay alive at the moment. Almost there. Hi, honey. No, everything's okay. No, nobody got hurt today. Well, except the, Remember how we were talking about getting me a new car? Touch potential is...
Okay, so a couple of things. Notice that when he touches the outside of the vehicle, as long as he's not touching the ground, he's perfectly fine. Because there's no potential difference between the inside of the car and the outside of the car. Potential difference implies that there are regions of charge separation. There's no net charge inside, there's only charge outside, which means that there is no charge separation between inside and outside of the car. Okay, so if that's the case, there's no potential difference. There's no reason for the charges to go through your body. That's what it means. The problem happens when he steps outside. Now the ground is uncharged and this region is charged, so there's a huge separation of charges, okay? So there's a huge voltage potential difference. So voltage potential difference implies the bigger the voltage difference is, the stronger the electric field is, as faster the charges are going through your body, which means that you will get shocked. So that you cannot do. All right, so the best thing to do is, obviously you have to jump away from the car, and when you do that, you cannot walk. The reason why you cannot walk is because there's going to be a potential difference between the car and any distance away from the car. All right, so potential difference is going to get weaker as you start to move, potentially gets weaker as you start to move away from the car. So if there's any sort of potential difference between these contact points, the charges are going to be forced to go through your body. So in fact, the bigger your step size is, the bigger the voltage potential difference is, the more charges are getting forced to go through your body. All right, so they refer to this as step potential normally. The other one is called the contact potential. It makes no difference. So the potential difference depends on the distance between the contact points and the strength of the electric field in between. So closer you are to the source of the charge, the stronger the field is going to be. And the bigger the distance between the contact points, once again, the bigger the voltage potential difference is going to be, the more charges will go through your body. So the best thing to do is keep your feet together. Okay, so when you keep the feet together, obviously the separation distance is going to be smaller. Voltage difference is going to be smaller. Okay, the current is still going to go through your body, but you won't feel it. It's going to be smaller. All right, so that's one way of doing it. You don't want to be falling on the ground because your head and then the bottom of your body could be at different voltages or potentials, which means that you will get shocked. So that becomes a problem. All right, this video was well done. Here's a second one.
Most of the time,
public safety
power lines
reasons.
stay safely out of our way, but sometimes storms or accidents can knock down lines. If a power line falls across your car, do you know what to do? If your car is still drivable, simply pull out from under the wire. If your car is disabled, the most important thing to do is to stay inside. Use your cell phone to call for help. Keep others away from the car. Only get out when utility workers tell you it's safe. Never touch the car and the ground at the same time. The only time you should get out is if there's imminent danger, like fire. Open the door fully. Do not step out. Stand on the metal framing of the car. Keep your hands close to your body to avoid touching the car and the ground at the same time. Slide your feet together. Hop off with both feet. Hop away from the car, keeping your feet together. At a safe distance, slowly spread your feet apart. If you feel a tingle, put your feet back together and hop further away. For EMC TV, this is Greg Brooks.
Okay, so a couple of things.
Slide your feet together.
Okay, so keep the feet together and then jump. Okay, so the problem here is when you jump, if you lose your balance, that's going to be a huge problem. Okay, hopping is you could do that or shuffle. Either way, it's going to work. The problem with hopping is it depends on your coordination. Some people are not as coordinated as some other people, so that becomes a problem. Another thing that I don't like about this is lack of understanding of physics gets in the way. Because if there's a power line on the car, just drive. There's no reason to stop. All right, just drive. Because when you stop, or just back off. You either go forward or go backward. Nothing is going to happen to the engine. Nothing ever happens. Just drive away. If you see a power line on the ground, don't walk towards it. Okay, so for whatever reason, if there's a power line and you decide to back off, don't get out of the car. Unless the whole system is de-energized. Don't do that.